Previously, we have covered step 1 and step 2 in the proof of transversality homotopy theorem. So now we're gonna go to step 3. But first, let us recap what we did. Let's recall the statement of this theorem. So we have a smooth map from a manifold M into a manifold N. For example, it could look like this. We have a given submanifold Z of N. Now, Z and F might not be transversal, but the claim is that we can always deform F to a homotopic map that is transversal to Z. Now, in part 1, we have shown that we can extend this map F to a family of map indexed by some smooth manifold S, such that this family, viewed as a map itself, is transversal to Z. Now, in step 2, we show that every map in this family is gonna be they are gonna be homotopic to each other, and in particular to the little f. Thus now it remains to show that at least one family member, one map in this family, is transversal to Z. But we'll prove something stronger. We actually show that most of these maps are gonna be transversal to Z. This is the content of the parametric transversality theorem. The parametric transversality theorem says that if the family F here is transversal to Z, then most of the family members are going to be transversal to Z. That is, for almost all little s here in S, the map Fs is going to be transversal to Z. Now, what does almost all mean? That means outside a set of measure 0. What's a measure on a manifold? Well, assuming that you know measure theory on usual Euclidean space, then note that the set S that we constructed in step 1 was just a ball in some Euclidean space, so we can talk about sets of measure 0 in that S. But more generally, if we have just a general manifold, we can use chart to carry over the notion of measure 0 sets onto the manifold. But we don't need the detail of that now, because we're just gonna take this S to be the Euclidean ball anyway. Alright, but now let's come back to the theorem. So the theorem said that for almost all little s here, in this big S, we have that the map F little s is gonna be transversal to Z. Well, to prove this theorem, it suffices to actually just show that for a given point little s here, in this big S, this map F little s is going to be transversal to Z if the projection map from the preimage of Z, right, onto S has this little s as a regular value. In other words, a sufficient condition for this map F little s to be transversal to Z is that this little s is a regular value of some map. So why would this imply the parametric transversality theorem? Well, that's because of something called the Sard's theorem, which says that given a smooth map pi, right, to some manifold S, then almost all points of this manifold S are going to be regular value of pi. Putting it in another way, we could say that the set of critical points of any smooth map must have measure 0. In particular, most points of S are going to be regular value of this map pi. So if this statement here holds true, then for most points little s in S, the corresponding map F little s here is going to be transversal to Z, which proves the parametric transversality theorem. So now let us prove this statement. And again, let's recall what this map pi is. On this product S times M, we have a projection map to S. Pi is just going to be defined to be the restriction of that projection map to the preimage of Z. So now let's suppose that this little s is a regular value of this map pi. That means that for every point P in the preimage of this little s under pi, we should have that the tangent space to F inverse Z at P surjects to the tangent space to this big S at little s. In this picture, for example, I have drawn as if there are 2 points, P and Q, in the fiber over this little s, the fiber under the map pi. Alright, so that's the hypothesis. We're assuming that this letter S is a regular value of this projection map pi. Now we want to show that this map F letter S here is transversal to Z. Well, what does that mean? What does it mean for this map Fs to be transversal to Z? Well, it means that for every point P here in the preimage of Z under Fs, we should have that the tangent space to Z at Fp together with the image of the tangent space to M at Fp, so this image here, together this should span the tangent space to N at Fp. So together they should span this tangent space. Okay, and now comes the part when we'll be extremely hand-wavy. We will do the worst thing, we will just prove by picture, just to have a general intuition. Right, so the idea is because this little s is a regular value of pi, we know that this tangent space here surjects into here. Right, but that means that together, this tangent space here and this horizontal tangent space here, together they span the tangent space to the product s times m at p, this whole tangent space. That means that their image under the derivative of this map at P should span the image of this whole tangent space at P, right? So that means that these two tangent space here should span the image of this whole big tangent space, the tangent space to the product at P, right? And the tangent space to Z at FSP. So this. But those two together span the tangent space to N at Fp because we have assumed that the family is transversal to Z. And so we have very sloppily show that if S here, letter S here is a regular value of this pi, then F letter S is going to be transversal to Z. Now by Sard's theorem, we know that most letter S in this big S are going to be regular value of pi. So then we see that for almost all letter S in this big S, this F letter S is gonna be transversal to Z. In other words, most members of this family of maps are gonna be transversal to Z. Now coming back to our proof, remember we have constructed a family of map homotopic to F, right? Such that this whole family is transversal to Z. Now, by the parametric transversality theorem, we know that most members in this family are going to be transversal to Z. So then that means we have a bunch of maps that are homotopic to F and transversal to Z. Thus, we have proven that there are many ways to deform F in a way that is transversal to Z. And that concludes our proof of transversality homotopy theorem. So now we can move on to talk about intersection theory.